Then we still have some lecture summary sheet here. Team 3, 4, and 9. Okay, I'd like to begin to mention something that most will be interesting. On Monday, I will be presenting at the conference on Monday. So I have here my lecture notes and the video that you can view on your own. Okay, and I will talk about the Beatles topics today. All right, and also there's a lot that I can talk about, but due to the time, we don't have much more time. So I'd like to mention to you about something that many of you are interested. Okay, and that's regarding the exam and the review. Okay, so let me zoom in here a little more. For exam 2.1, which is on Friday of next week, right? So the review will be on Wednesday, and the focus will be on problem 1 or problem 2, okay, of the exam statement 2.1. I have gone through these problems and we'll do a review. For exam, sorry, this is 2.2. I was just copying and pasting, and I have not changed that. Exam 2.2 will be on Wednesday of week 15, and the review on Monday. And the focus will be on problem 2 or problem 4. All right. And I talk about problem 3 today. Okay, so this is also related to the report problem 5.6, and I listed here the links to the appropriate sections that would help you to do this problem. You have the best solutions and a solution guide. Okay, and I will talk about some of these aspects, and I have the videos also associated with this lecture from last semester. So if you need, you can also view the video. Okay, so problem 3, and these are the related, handwritten notes that I have, section number, and later on, as I mentioned, I have also the videos. Okay. Let me show you the videos maybe on this side, and perhaps 100%, and I go up. Okay, so you see here I have listed, for example, section 25H, 25D, 25E, and below here. This morning I spent some time actually to really annotate the video. Let me zoom in. So you see, I even, for example, for the video of the meeting 48 in IEA 2014, this is the content. I even indicate the time, right? The time station where I talk about certain part. Okay, so it's very detailed. You can do that. So now what I'm doing in this lecture is to really give you the big picture, and the most, I think this is as real world as it can be. The application is on music note detection, application of fast Fourier transform, and you will see. Okay, so this is a long version of my talk. I have more slides than then I can talk within 20 minutes or 15 minutes at the conference. Okay, so here it goes. In last semester, I did much more detail than this, and you have my lecture videos from last semester, so you can also view for those of you who are interested. I have already talked about this, both the movie and the songs are classics. Okay, I already talked about this. So this is the content of the course. In the first half of the semester, I focus on the system of linear second order ODEs, focusing on the model superposition technique that I checked with some students who take preparation. They just finished this part in the second half. But what we did is even more advanced, namely the second part, because what they learn in vibration cannot solve advanced function. For example, logarithm or exponential or even much more complicated function, because the tool that allows you to solve analytically when the system is excited by advanced function is in the second half of the semester. It consists of, essentially the idea is projection, and projection on two types of bases, right? The polynomial basis, and the equivalent of the polynomial basis is the oblique coordinate system in vector space, and projection on Fourier basis, and the equivalent is projection on Cartesian orthogonal coordinates in vector space. Okay, and I take the Fourier analysis would be Fourier series and all of the topics leading up towards fast Fourier transform, but I can only show you the application. Okay. In spring 2014, when I was teaching also in this room here, I was waiting outside, and a student told me that he took the course and he could not connect with, in a different section, he could not connect IEA with application. So I decided that I don't want to teach a mathematics course for engineers, but I want to teach an engineering course with mathematics as a fundamental tool. Okay, and that's what I did from 2014, including this semester. And you may remember that, I'm sure, that I use a lot of real-world problems to motivate, from the Tacoma, from the longest suspension bridge, the Akashi-Kaiko Bridge, to the collapse of the Tacoma Narrows Bridge. I mentioned often about the large application of finite elements, satellites, train, vehicle, and so on and so forth. I also use earthquake analysis with soil structure interaction to motivate. This is the classification from fall 2014. There were 85 respondents out of more than 100 students, mostly junior, senior. I have 2 PhD students. So you see the level is really, ranging from across from junior to PhD. Most 80% say that they took the course because it's required. About less than 18% said that it's required and they are also interested. These 2 students were PhD students. They took the course because they were interested. Okay, and the expected grade, those who responded expected high grade. This I already mentioned, 85% took the course because it's required, and about 50%. If we take also those who did not respond to the survey, that they took the course because it's required and they are interested, and probably the reason is because there's a lot of math in this course. You can confirm that maybe. But this is the only thing that I can think of. And even though I started all topics with application, everything always started with engineering application. But math is a tool. So I was thinking, what other applications that I can use to excite students, with diverse interests, technical backgrounds, preparedness. and level, as you saw there. Okay, even if there were no PhD students, the level would be quite different. And so I was searching and I came across in spring 2014 this paper by Brown, 2004, a mathematician from Canada. And if you look at the title, you know, mathematics, physics, and a hot day's night. Sounds like a perfect topic, you know, because it includes math, physics, or engineering, and rock and roll, right? So in the abstract of the article, you read, we shall use mathematics and the physics of sound to unravel one of the mysteries of rock and roll, right? How did the Beatles play the opening chord of A Hot Day's Night? The song may never sound the same to you again, meaning once you understood this paper. Right? So I found that, wow, this is great. You know, this is combine all of the exciting ingredients. It's a detective story. You know, it should be of interest to many, right? Younger or older. Right? It's music. It's rock and roll. It's the Beatles. I mean, I'm sure it's impossible not to know who the Beatles were, right? So that should be a topic that would excite many, if not most. And it's math and physics. This is really directly related to the course. So music, rock and roll could be a magic answer, you know, to really excite students to learn. But there were hurdles. I show you the hurdles. So the hurdles, you know, you saw I link to my daily lecture summary, the paper. So when you look at the paper, you see what? You see the music letter notation. In fall 2014, more than half the class cannot read music score. And then you have the music staff graphical notation. Then you have the guitar tablature notation. Right? This is for the guitars. And then you also have something that really confusing. Guitar parts are scored as usual and octave up from where they sound. Why? You know? So all of these have to be explained, because my goal is, you know, I want to help students understand the paper and enjoy the paper, you know, like I did. But I was not prepared to teach the topic back in spring 2014, just because that I had mentioned half the class cannot read, and therefore there's a lot of preparation to explain all of the music notation, the music graphical notation, guitar tablature, and clarify why the guitar score is scored at one octave above from where they sound. Okay? So here another thing, another hurdle. This is how Brown did the work. You know, he recorded the sound and used Mathematica routines to do FFT analysis, and just present the results as a list of numbers. You know? Mathematica was not available to all of you. I can also replicate the steps here using MATLAB, but it's really laborious. It's time-consuming, and you know, and labor-intensive. And you know how you would like, right? Something quick and faster, and get the result. So this is really a hurdle, because if we go through all of these, it does take time. I enjoy it, but maybe not many other graduates. Okay. So I spent a lot of time learning myself. I just had the basic music education. I learned a lot by reading this paper, and put a lot of annotation so to help students to understand. Okay. And the software that I use is Audacity. You know, I have experience with this software long before the Beatles topic came up. You know, every day you see that I try to record all of my lectures, and I started this back since spring 2012. All right, and so I was already familiar with this tool, and I discovered that actually it already has the fast Fourier transform analysis built into it with very nice graphical user interface, and students can record the sound, do FFT analysis with the graphical representation of the FFT spectrum. And so that is for a course, you know, not a refined level of music detection. If you want to do a more accurate music detection, you can download the numerical fast Fourier transform spectrum and use the spreadsheet to identify the music notes, and that's what you started with the spreadsheet. And if you read further into the paper, you see many concepts that if one does not have an education in music, it would be hard to understand this paper. Well, you know, you start, what is A220, right? So what is this strange formula, which now you should be familiar with? That's related to the 12-tone equal temperament scale, okay? And so what's a semitone? What are these numbers? Okay, these numbers are essentially represents the number of semitone. But why are they not integers, exact integers? Why are there you know, decimal digits behind that? That's because of mistuning. Okay, and what are these notation? You know, these are actually the music note scientific notation that I already explained in a lecture, where the letter represents a key in an octave and the number represents the octave number. So there's a lot of concepts that I taught students in the fall 2014, and it's recorded on video, not in this semester though, because I decided that I changed the way I taught. I give you the solution guides, the best solutions, the best report from last semester that level the playing field. How many of you heard about Chegg.com? Chegg.com. I'm sure most students heard about it. So I'd like to replicate something like that by leveling the playing field. I also spent a lot of time coaching students to solve the exam problem, which I didn't do last semester. Last semester they did not have the solution guides for the report. They did not have the exam statement, and I did not coach. So that's why I had more time to teach about the Beatles topic. So here I just want to give a quick rundown, and so you have the big picture of what this is about. It's very, very detailed. So this, this is just to, I was very ambitious because I want students to also understand the musical staff representation. Okay, being able to read the music score and connect that to the piano key, introduce some terminology that requires to understand the paper by Brown. For example, what's a fret and what are the strings in a guitar, the open strings, what these strings correspond to the music notes, and when you press on the fret, and what kind of sound would you hear, right? So, and this is for me to explain the guitar tablature and the correspondence with the strings in the guitar. Okay, I'm not going through the details here. The details will be in my video of my lectures in fall 2014. But you can sort of have a feel that there's a lot of details that needs to go through, okay, to really appreciate and enjoy the paper. So here, Brown, Jason Brown, professor in math, presented 3 versions of the opening chord, the transcriptions that he found on the internet. And his own version is the 4th version. Okay, so this is the first version here, the simplest to play. And this is the simplest because it involves only one 6-string guitar. And if you understand the guitar tablature, you see the number 3 here means fret number 3. And you see that all of these are number 3, so that means that you use your index finger, press on fret number 3. In the guitar jargon, it's called the barré. Barré is a French word, so that's how it's pronounced. And so that's why it's very simple to play. You just press your index finger on all of these guitar strings on fret number 3, and that translates to all of these musical notes that correspond to the music note staff graphical representation. Okay, so I explained all that to the student, but I want you to keep this in mind. You see there's a presence of the sound. Yeah, as I mentioned to you, the guitar is scored at 1 octave above where it sounds. So the sound or the FFT would recognize the sound G2, but in the music score you would read G3. Okay, that's just keep that in mind, just a detail, but this is more important here. Brown used the fact that there's a note G2, the sound G2, in all of the 3 versions that he found on the web. Okay, but his version, or at least the recording that he used, did not have the note G2. That's how he eliminated all of the 3 versions, the 3 transcriptions of the opening chord on the web. Okay, so that's something you want to keep in mind. And here I continue to explain to students, because when you read in Brown, he described the range of the guitar. A guitar would be able to, electric guitar would be able to play sound from certain note to certain note, and the bass guitar that would be able to play the notes from certain range, E1 to D4, because Paul McCartney plays a bass guitar, where John Lennon would be the 6-string guitar, and George Harrison would be a 12-string guitar. Right? So all of that is described in Brown's paper. You see, so this is the real world, because you don't just use the sound. You need to use knowledge from elsewhere. For example, knowledge of the musical instrument. You need to understand the construction of the piano in order to do detection. So it's not just processing the signal from the sound. You need more than that. Okay. That's why you may recall that I said that the input data is not sufficient in real-world problem. You need more than that, Paul.
So, were you saying like they still haven't figured out what the chords that they play?
Yeah, we'll come to that. It's a very good question, Paul. In fact, even I will show you here that another aspect of real-world problem is that the solution is not unique. Okay, you can have several arrangements that the ear would hear the same thing. Okay, we get into what is called psychoacoustic, and I'll get to that. Okay. There's still discussion on the web of how to play the chord, and the paper by Brown is very well known.
Yeah, because I was going to say, like, there's different ways to play the same chord, and depending on, like, exactly the way his guitar sounds, it's going to sound different than a different guitar, so, like, to replicate it perfectly is never going to happen.
But, you can still do something that the ear can perceive as similar. Okay?
Right.
But what I'm trying to say is that you will see that the solution is not unique, and I've shown it to you why. Okay. So this is what Brown had in his paper. You see, just numbers. But what you want to keep in mind is that an FFT spectrum, you have the frequencies, and you have the amplitude of vibration. Okay, so these numbers represent the amplitude of vibration. 2 things you want to keep in mind. The largest amplitude correspond to the D3 note, and the smallest amplitude is about 0.02. Largest amplitude is 0.18. The ratio is about 10. Okay, keep that in mind. The ratio is about 10. It's like 0.2. 0.2 divided by 0.02, so 10. Okay, so I have the this lecture notes that I show to students how to install and use Audacity. So when you do problem 5.6, you need to install Audacity, and so this is very detailed. Okay, and I also show to you the video of my lecture on this, but the lecture notes is very clear. So all of you are STEM students, and you can install and use software without difficulty. There are 2 methods to record sound. I will not go deep into this So this is what you would see when you run FFT on Audacity. With Audacity, this is a pure sound, basically a sine wave. You see the amplitude is constant. A real piano sound, you will see there's a damping. Okay, but you see, look at the vertical axis here. This is the graphical representation of fast Fourier transform. The vertical axis, the unit is in decibel. Okay, so this is an opportunity for me to introduce the concept of decibel. And you see, a decibel is related to the ratio of the amplitude. So if the ratio is 10, if A1 divided by A0 is 10, log base 10 of 10 is 1, 20 times 1 is 20. So from this, and by observing the FFT result of Brown, I deduce, I tell students, okay, from the peak note, reduce by 20 decibel, take a drop of 20 decibel, that's basically the cutoff. So any noise level below, I will have a slide where I show that, yeah, right here. So for example, this is the A4 sound from a sine wave, and you see, so that's the peak, and define the cutoff as 20 decibel from the peak note or the loudest note. Okay, so you see that for this A4 sound, below essentially there's no other sound, and this is just noise. With Audacity, it also gives you the note name. Okay, so at 440 Hertz, it gives you A4. So that's very convenient for students because you can do a quick detection with Audacity. Okay, using just the graphical representation. So this is the a simulated piano sound, A4 sound from software. It is very good. It's very well simulated, and this is the detail that I skip for now. For those of you who knows music, you know what's the A4 major chord is, and I showed to students. Even if you don't know music theory, you can still find out the notes within the A4 major chord just by looking at the fast Fourier transform spectrum. Okay, and just one thing to keep in mind: these are called the higher harmonics of the main frequency A4, of the main sound A4. Okay. So now this is related to a question in problem 3 in exam 2.2. Okay, and this is also has a nice historical story. Why do you have 12 tones, 12 semitones in an octave? Okay, and that dates back to Pythagoras. In music, you want to search for tones that sounds nice together, right? It's called consonant notes. Notes are consonant sounds nice together, and that's when the octave came in. You know, what is an octave? If you take a string and you cut in half, right? The frequency would be increased by 2, and when you play these two notes, they sound nice together. But an octave is too far. You know, music is not rich enough if you have only the notes at the octave. Okay, so you need to fill in between two notes that separate by 1 octave by more notes. Okay, so that you have a richer music. An example, for example, if you look at A4, right? A4 and A5. A4 is at 440 Hertz. That's the pitch standard where all concert instruments are tuned exactly at 440. Then A5 is at 880, right? 880 is 2 times 440. But if you just have only these two notes, the music is too poor. So you want to fill in inside the octave range or interval more notes. So came next the discovery. This is an important discovery of Pythagoras. By the way, we should call the Pythagoreans because the Pythagoreans formed like a sect led by Pythagoras. Okay, and the discovery is often associated with Pythagoras, but could be made by a Pythagorean. three important discoveries. You know Pythagoras theorem. That's very important. And the second one is the irrational number, square root of 2. And the third one is the music scale, right? The magic factor 3/2. What Pythagoras or Pythagoreans discover is that if you take a string and multiply by 3/2 or reduce by 3/2, when you play these two sounds, they sound nice together. Or these two notes are consonant. So the Pythagoreans use the factor 3/2 to construct the scale. It's called the Pythagorean scale, and this is based on this formula here. Okay, let's follow me on just on the column here. The first column represents the value for n, and the second column represents the value for n. The method is very simple. You take the fundamental frequency, start at 440, you multiply by 3/2, and so for the first time, when you multiply by 3/2, it's still within the octave, you know, and 3/2 is 1.5, and you get 660. It's less than 880, right? So it's within the octave. And then you keep multiplying by 3/2. So the second time you multiply 3/2, and then multiply by 3/2 once more. Then it falls outside the octave. If you want to move back or map back to the octave, you need to divide by 2. Okay, because an octave is either by multiplying the frequency by 2 or divide by 2. Okay, so for the second step here, you multiply the fundamental frequency 440 by 3/2 to the power 2, and then divide by 2. What you get is 495 hertz, and you keep doing so. And but the problem is the following: when you reach to the 12th semitone, it turns out that you get 892 hertz instead of 880 hertz. That is the inconsistency between the Pythagorean scale and the octave. Well, actually, it's called the perfect fifth. There's a reason for that. So, and the octave, there's this inconsistency led to something that in music and also in engineering, a very important concept called the Wolf fifth. The Wolf fifth, Wolf is because of the mismatch in the frequency. Just, you know, if you play two sounds with two frequencies that are close to each other, there's a beat phenomenon, and it sounds like the howling of a wolf. That's why this interval is called a wolf fifth. And let me, you know, in my daily lecture summary, there's a link to the sound where you can hear the beat phenomenon. Okay, so I just so now. What is the 12 tone equal temperament? 12 tone equal temperament was created to avoid the mismatch, to avoid the wolf fifth. So that you fall after 12 semitone, you fall exactly on 880 hertz. And equal temperament because on the log scale it's equal. Okay, so that's why it's called equal temperament. So the 12 tone equal temperament is actually a massive compromise between the octave and the perfect fifth, because you cannot have both, you can only have one. That's all I want to say about this. These formulas I already mentioned to you. And here I show the student how to detect the first chord, the notes in the first chord of a piano classical music. This is very beautiful. I have the recording on the daily lecture summary that you can play and listen to. And so this is the FFT spectrum, where the peak note is C4, and 20 decibel below the peak note is the cutoff, and so you would retain only these notes. Okay. So let me see. Okay, I have 15 more minutes. Okay, so this is basically the algorithm that I taught students on how to eliminate notes. Essentially, start with the peak note, eliminate the higher harmonics, and you know, retain the lower frequency and so on and so forth. There's more than that. And after you obtain the plausible notes, and you still need to choose you know, 6 or 7 notes to play. And this is what I replied to Paul, that you can have several arrangements that have basically the ear would perceive a similar sound. So this is an example of the elimination. I will not go through the details. You know, you can see that there is a stage where you need to eliminate the higher harmonics. You need to identify the pitch class. What's the pitch class? A pitch class, for example, here you see C, D sharp, and G. You have C2, C3, by C4, C5. All of these differ by a multiple of octave and form what we call a pitch class. Okay, and then there's some single notes and there's major chord, but this is what you want to keep in mind. These are the notes that retain after you apply the elimination algorithm, and comes the selection of 6 or 7 notes out of these 1, 2, 3, 4, 5, 6, 7, 8 notes that remains. Okay, so here is an interesting the beginning of the answer to Paul's question. Okay, I collaborate with a concert pianist. She has a PhD in performing arts. She also a concert pianist. But what differs her from many is that she has a perfect pitch. A person with a perfect pitch or absolute pitch is someone who can, just by listening to the sound, tell you exactly what the note is. So I created the pure sound. I used Audacity. I created a pure sound with very low frequency, A flat 2. She just listened to that and she said A2. See, that differed by only a semitone. This is very low frequency. I have the recording, you can play, it's very low. And then, you know, I use a very high frequency, E flat 6, and she detected E flat 5. And you see these two notes belong to the same pitch class. I told you a story, I think I have also a link in my note, that this is something called the octave equivalence. You know, there's a song called Happy Birthday, and with certain notes, you just displace by 1 octave above or 1 octave below, and when you play the sound, you can still identify that's the Happy Birthday sound. Okay? So that's the so-called octave equivalence. And then for the pitch standard 440, she, you know, basically identified immediately. And I asked her to detect the notes for this recording of the Beatles opening chord. You see that she detected C3, G3, C4, and D sharp 4. 4 different notes. That's pretty difficult. Okay, and look at the FFT spectrum. You have C3, G3, C4, and D sharp 4. And then you have many other notes, right? And going through the elimination algorithm that I've taught students, these are the remaining notes, right? 1, 2, 3, 4, 5, 6, 7, 8 notes. One of the choice would be, let's say, remove C2, because note that C2, C3, and C4 belongs to the same pitch class. And the ear can feel it, even if you miss certain notes in the same pitch class. So one choice. Remove C2, let the left hand plays C3 to G3, and this is less than 1 octave, and a span of my hand, I can span a little more than 1 octave. So this is playable. And on the right hand, now this is a stretch. From C4, D sharp 4, G4, and you see C5 is right here, and D5. So this is more than 1 octave. And so I asked my Austrian collaborator, his girlfriend was learning piano, and this is her piano teacher, and he can try that for me, and indeed he can span going from C4 to D5. Okay, so this is called playability. So not only that you select the note, but you need to consider whether that is playable or not. And then I have problems for students to do. Actually, In this semester, you only do problem 1 and problem 2. In last semester, they did also problem 3. I plan not to have report 6, so report 5 will be the last one. And also I did a psychoacoustic experiment, and I'd like to describe to you what it is. So this is, I showed the student how I identify the notes in this recording of the Beatles. It's a Beatles Anthology 1 CD. But you see, all I want to show to you here is this is Brown's result, with A2 being the lowest note. But you see, look here. After I do the cutoff, A2 is very low, below the cutoff. That means that the sound is not loud enough. It's actually too low. But I have other notes that are, that you can hear, audible, right? So clearly this recording was not what Brown used. So you see, at first I thought, wow, if I pick up any of the Beatles recording of A Hard Day's Night, I should be able to replicate what Brown had in his paper. That's not true. You see, each recording would give you a different signature, a different fast Fourier transform spectrum. Okay, that's the lesson that I learned. And I tried with 2 more. One from Wikipedia, which they did not say where they got the recording from, and another from YouTube. Okay, and all not correspond to Brown's results here. And Brown did not even mention in his paper which recording that he used. Jackie?
What about the difference in digitizing?
Sorry?
What about the difference in digitizing?
The difference in?
So you take the same analog sound, you're digitizing, right?
Yeah, these are all digital sound. Yeah.
So what about the difference in the actual digital process? Could that be the result? Could that be
For the difference?
Yeah.
That could, maybe, I don't know. I'm not an expert in that area, so I just select all the digital sound that I can get my hand on. Actually, here for the Beatles Anthology 1 CD, I had to go to a library in Urbana, Illinois, where my family is, and borrow the CD and record with Audacity. I formed a rock band, composed of all students in the class. We have a 12-string guitar representing George Harrison. We have a Hofner bass guitar representing Paul McCartney. I had 2 6-string guitars representing John Lennon. So the position of the students described here, and the electric keyboard. So here is the key of Brown's paper. Brown analyzed the fast Fourier transform, and with his knowledge of the piano, right, the physics of the piano, deduced that there was a piano that was being played alongside with the Beatles. That was the discovery. Okay, and it turns out that that's true because George Martin was the producer of the Beatles and often played along with the Beatles, and so the opening chord had the presence of the piano. That was from Brown's analysis. And psychoacoustic survey. So I had the rock band play 4 different versions, scrambled, and not letting the class know which order. And I asked the class whether they can distinguish the 4 different versions. You see, the answer is all over the place. That tells you that that's the psychoacoustic effect. Okay, the ears cannot perceive the sound as FFT, right? And answer to you. And even a concert pianist with perfect pitch can only detect 4 notes accurately. Regular people like us, it would be impossible. So that's why everything we hear sounds similar, and that's why on the web there's so many different versions. 50 years after the release of the song. Now this is also exciting to me. This is Richard Feynman. So not only we have the Beatles, we have Richard Feynman. think it's getting noisy. Let's see, let me check how much time I have. 40, okay. You see, I won't be able to go deep into this, but this is a letter that, this is the handwriting of Richard Feynman. The author of that article in Physics Today sent me a copy of his letter, and this is what you see. This is the handwriting of the genius. You see it's cursive, it's slanted, and he derived the equations, okay, that I did we derive for students. I don't have time to get into the details, but this is the lecture note that you see in my list of topics, okay? This is, you have the bending stiffness, that's why you have something called inharmonicity. That's a very important effect in piano. But let me mention the following. Feynman, not only it was a genius, but he was also, has a humanity. You know, he wrote to his piano tuner and used the quantities that the piano tuner would understand. For example, in the formula that he described the inharmonicity of the piano string, you see, he used various different units that the piano tuner would understand. And through my lecture notes, students also learn to do dimensional analysis and non-dimensionalization. Okay, so here, maybe this is time to look at this. You have seen, this is the survey. About 80% were not interested, but you see after the Beatles topic, you see this is more life here. You know, over here it's more anemic. It's no life. It's one-sided. But here, you know, this distribution is more real, where more than 40% indicate that their interest in the course have increased because of the Beatles topic. Whereas there's some who, you know, who said that the interest decreased, and I guess it's because of the heavy music theory aspect. That's why you see I have already scaled it down. But you can see the effect that it is, and so now let me close. It's a real-world problem, right? It's complex, challenging, messy, interdisciplinary. The input data is not sufficient. You need to know other areas, and output data is more than necessary. You need to eliminate and select data. You have mathematics aspect, physics and engineering, and you have Richard Feynman. You know, not just the Beatles. And then the music theory has it basically applied acoustics, and there's a psychoacoustic experiment, which is very important aspect to understand why there's so many different transcriptions. It's rock and roll, that's great music, and the movie. Now the caveat is that many students cannot read music and are not open to learning. And so in this semester I have scaled down the music aspect. Okay, so that's the big picture for the class, condensed into 40-45 minutes. Okay, lecture summary, everyone. I'm very excited about this, so I hope that some of you will find this interesting.